Alright, so we had done quite a few things in the previous few classes. What we would like to do is that I would like to first do some exercises related with QR decomposition, and if time permits, then we will look at some ideas that I have missed. Otherwise, I will do that in the next class. Alright, so let me look at some of the examples for QR decomposition. So examples. So the first example is, let A is equal to 1 0 1 0 0 1 0 1 1 minus 1 1 1 2 1 1 1. All right, fine. Question is, find an orthonormal matrix Q. So I write it as orthogonal because that's the way it's written there in the orthogonal matrix Q, and an upper triangular matrix R such that A is equal to QR. Alright, so let's look at the solution. So now the ordering is fixed. There is a first column, second column, third column and fourth column. So you'll have to go and do your calculation based on that itself. So you'll have to write U1 as 1 0 1 0, U2 as 0 1 0 1, U3 as 1 minus 1 1 1 and U4 as 2 1 1 1. Alright, this is the way we are supposed to do. So from here I get W1 as 1 upon root 2 times 1 0 1 0. What about W2? So look at U2, and this, the inner product between U1 and U2 is already 0. So W2 is equal to 1 upon root 2 times the same vector, 1 upon root 2 times 0 1 0 1. If I look at U3, alright, then U3 is already perpendicular to U2. You look at this, minus 1 1 and 1 1, that is 0. So but anyway I have to compute what is V2. So let me compute V2. V2 is, not V2, V3. So V3 is U3 minus U3 W1 W1 minus U3 W2 W2, which is same as 1 minus 1 1 1 minus inner product of U3 with W1. U3 with W1 is 1 into 1 plus 1 into 1, that is 2, and this square root of 2 comes twice, so you divide by 2 here, fine, and multiply by that. So it is 1 0 1 0 minus U3 with W2. U3 with W2, if you look, so 0 times 1, 1 times minus 1, and 1 times 1 will give me 0, so it is just 0 for us. It does not give me anything. So it is nothing but 1 minus 1 1 minus 1 0 1 0, which is equal to 1 minus 1 is 0, minus 1 minus is minus 1, 1 minus 1 is 0, and 1 here, fine. So be careful, I always do mistakes, as I said. So I define W3 is equal to 1 upon root of 0 minus 1 0 1. So now I have to compute what is V4. So let's look at what is V4. So V4 is 2 1 1 1 minus V4 with W1 W1, V4 with W2 W2, and V4 with W3 W3. So this is equal to this vector 2 1 1 1 minus V4 with W1. So it is 2 plus 1, I think 2 plus 1 is 3, 3 upon 2 times 1 0 1 0 minus V4 with W2. V4 with W2 will be, I hope I am doing correctly, 2 plus 1, sorry, 1 plus 1 is 2, so it is just 0 1 0 1 minus V4 with W3. V4 with W3 is minus 1 here and 2 minus 1 is so 0 0 minus 1 0 1, so it is 0 here. Fine. So this is equal to, let me write in terms of the row vector, 2 1 1 1 transpose minus 3 upon 2, alright, so 3 upon 2 0, 3 upon 2 0 minus 0 1 0 1, which is equal to 2 minus 3 by 2 is half, alright, 2 minus 3 by 2 is half, 1 minus 1 is 0, 1 minus 3 by 2 is minus 1, so minus half, 1 minus 3 by 2 is minus half and that is 0, 1 minus 1 is 0. So this is what I get. Fine. So this will imply that W4 is 1 upon root 2 times 1 0, or since I am writing column, so let me write column itself, there is a space, 1 0 minus 1 0. Alright. So this is what I get, W1, W3, W3 and this. Fine. W4. Is that okay? So therefore what I get is Q4, or the matrix Q is nothing but, look at, so I think I should write somewhere here. So Q is 1 upon root 2 0, 1 upon root 2 0, that is the first vector. Second vector is 0, 1 upon root 2 0, 1 upon root 2. The third vector W3 is 0 minus 1 upon root 2 0, 1 upon root 2, and the fourth vector is 1 upon root 2 0 minus 1 upon root 2 0. This is what Q is. I need an R here and I have an A here. A is given to be equal to 1 0 1 0, 0 1 0 1, 1 minus 1 1 1 and 2 1 1 1. Alright. So to get the value of R, as I said, these are orthonormal. So you just have to look at inner product of Q, the first column with the first column here and so on. Alright. So if you look at the dot product here, it is root 2 for you. Alright. Fine. So look at 1 upon root 2 plus 1 upon root 2. So you get root 2. So this entry is root 2, and since I am looking at Gram-Schmidt's process where the linear span remains the same till the ith stage, so I get this as 0 here. There is no contribution from the second, third and fourth column. Fine. Now if I want to look at the second entry here, I will have to look at inner product of this with the second one and this with the second one. So this with the second one is already 0, this is only this one which is playing the role. So it is nothing but 0 root 2 0 0. Similarly, let us look at now the third one. So I have to look at the inner product of this with this one. Inner product of this with this one is 1 upon root 2 plus 1 upon root 2, which is root 2. Inner product of the second vector, that is W2 with U3 is already 0, this is what we had seen. So this part will be 0. Fine. Similarly, I would like you to see that this is 0 here, 0 here. Fourth one, let us look at the fourth one. So fourth one has lot of entries, so be careful. So I have to compute fourth one, this is the fourth one. So U4 inner product with W1. So with W1 the inner product of this is 2 0 1. So 2 plus 1 3 upon root 2. Alright, so it is going to be, I am looking at this. So this into this should be 3 upon root 2, 2 plus 1, did I write it correctly? I think I have written it wrongly there, so it should be 3 upon root 2 here. Fine. This with this one will give me 2 1 0 root 2, so it will give me root 2. Fine. So basically you have to compute things. This with this will give me 0 minus root 2 0 minus here, so that goes off. This is 2 plus 1, so it is 1 upon root 3 here, fine. So 1 upon root 2, just look at it, 2, 0, 1, so 2 upon root 2 and 1 upon root 2 is 1 upon root 2, 0, alright. So verify, I may have done mistake as verify, because my notes show something else, so I am sure that I have done a mistake, so verify it, alright. Very, very important verification, alright, you have to do that. So what we have seen here is that here I have got a Q which is A is 4 cross 4, this Q is also 4 cross 4, and therefore this implies that A is linearly independent. This implies A is linearly independent, fine. So it gives me linear independence as well as a matrix which is orthonormal. Q is orthonormal and I have got the matrix Q, fine. Let's look at another example, slide change. So example 2, I take A as 1 minus 1 1 1, 1 0 1 0, 1 minus 2 1 2, 0 1 0 1. So again I have got 4 of them, first, second, third, fourth, alright. We will see what we need. We want Q and R again, alright. So for me W1 will be equal to 1 plus 1 2 plus 3 plus 1 4, so 1 upon 2 times 1 minus 1 1 1. If I look at these two, alright, these two, they are not perpendicular, so I will have to compute V2. So V2 is 1 0 1 0 minus dot product of these two, which is 1 plus 1 2, basically with this W1. So V2 W1 W1, which is equal to 1 0 1 0 minus this with this is 1 plus 1 is 2 upon 2 is 1. So it is 1 minus 1 1 1, which is 1 minus 1 is 0, 1, 1 minus 1 is 0, and this is minus 1. So W2 is 1 upon root 2 times 0 1 0 minus 1. I hope I am doing correctly, because as I said, I am good at it. No, I have got something else here in my notes. V2 is 1 0 1 0, yes. So I get V2 as 1 1 1 minus 1. So where is the mistake? So this with this I have to do V2 with W1. So 1 here, oh, there will be 1 upon 4 here. See, W2, 1 is 2 here, so there will be a 2 coming here, 2 coming here, so it will be 1 upon 4. So it should be half here. Alright, so as I said, I am good at mistakes. So I may have done similar mistake earlier also. So be careful. So it is 1 minus half is half, 0 minus minus plus is half, 1 minus half is half, and 1 minus 0 minus half is minus half. Alright, fine. Now it's correct. So now, so W2 here is again, so it is 1 1 1 minus 1, so it will be 1 upon 2 times 1 1 1 minus 1. Alright, so this time my notes are correct, I think. So I have got this here, fine. So I have got W2. Let's get W3. So I have to go to V3. V3 is 1 minus 2 1 2 minus V3 with W1 W1 and V3 with W2 W2, which is equal to 1 minus 2 1 2 minus this with this will give me, so let's do this part, 1. So I am good at mistakes, so let me do it. I think 1 into 1 is 1, minus 2 and minus 1 is plus 2, 1 plus 1 is 1 and 2 here. So 2 4 6, 6 upon 4 times 1 minus 1 1 1, fine. With W2, if I see, it is 1 here, minus 2 here, so 1 minus 2, 1 minus 2 plus 1 and 2 minus 2 here. So 1 plus 1 is 2, 2 minus 2 is 0, so minus 2 upon 4 of 1 1 1 minus 1. So this turns out to be, I have written it as 0 1 0 1. So let's see. So this will cancel out. I get 3 upon 2 here. This will give me half. So I have got 1 minus 2 1 2 minus of 3 upon 2 minus minus plus 3 upon 2. So, with a minus sign here, then it is 3 upon 2 and 3 upon 2 minus half 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 minus half, and this is equal to 1 minus 3 by 2 and minus half, that is minus 1 I think I get here, minus 2 plus, so it is plus 3 by 2, so it will again be half. So, I think there is some mistake, I think again 1 minus 3 by 2 minus half I am getting here, and my note says something else. So, let me do it again, I think, as usual. So, I wrote it correctly, I think 1 minus 2 1 2, fine. So, I have to look at inner product of 1 minus 2 1 2, inner product with 1 minus 1 1 1 times 1 minus 1 1 1 divided by 4. So, this is 1 here plus 2 plus 1 plus 2, which is 3 by 2. So, minus 3 by 2 I wrote here, 1 minus 1 1 minus 1 I wrote it correctly, this part. The other part was V3 with this. So, it is 1 1 1. So, 1 minus 2 1 minus 2. So, minus half, or minus minus plus. So, there is a mistake here, it should have been a plus here, because there is a minus minus here. So, there is a minus 2 here. So, it should have been plus here, all right. So, therefore, there is a plus here. So, 1 minus 3 by 2 and plus half is 0, fine. Then 1 minus minus plus 3 by 2 and plus here, fine. So, look at this, 1 plus 3 by 2 and plus half, is that okay? So, it should be 2 here for me, 3 by 2 plus 1, so sorry, it will be 1 here. Then what am I doing? Let me write it, minus 2 plus 3 by 2 plus half, which is 0. Why did I write here 1 here? Again some mistake is there, I think. 1 1 minus 1 half, I got it as minus 2. So, minus minus plus and half of half will come into play, that is okay. Minus 3 by 2, 1 minus 1 1 1 here, 0 1. So, let us see what it is, fine. So, 1 plus 1 minus 3 by 2, whatever it is, 1 minus 3 by 2 plus half, 3 by 2, so it is 0 here. So, check what it is, this entry, all right, and 2 minus 3 by 2 minus half, which is 0 here. Oh, so it is already 0, so everything is 0 here, all right. So, everything is 0. So, it means the calculation was correct, fine, my notes are correct, it means. So, V3 is 0 implies that U3 belongs to linear span of W1 W2, this is what we will see also afterwards. So, I take the next vector as my V3 as 0 1 0 1 minus, so this was my U4, so I am looking at U4 here, U4 with W1 minus U4 with W2 and this gives me, my note says that this is equal to 0 1 0 1 transpose. So, I hope it is correct. So, I get that W3 is 0 1 0 1 and then there is this. So, 1 upon root 2 take care of this part. So, this is what my W is. So, try that out yourself, I think. So, what I get here is that I have the matrix A here, Q here, R here. So, Q for me is 1 upon 2 minus 1 upon 2, 1 upon 2, 1 upon 2, then it is 1 upon 2, 1 upon 2, 1 upon 2 minus 1 upon 2, 0, 1 upon root 2, 0, 1 upon root 2, this is what I have. A is already given to me, that 1 minus 1 1 1, 1 0 1 0, 1 minus 2 1 2, 0 1 0 1. So, I have to find this matrix Q. Again look at the dot product of this and verify that this turns out to be 2 0 0, 1 1 0, 3 minus 1 0 and 0 0 root 2. Alright, so please verify this yourself. So, what we are seeing here is that this is a 4 cross 4 matrix, this turns out to be a 4 cross 3 matrix and this is 3 cross 4, fine. So, this part tells me that rank of A is 3 and I would like you to verify that Q transpose Q is identity. Just verify it, verify, all right. And you can see that this matrix in general it is not upper triangular, but it has an upper triangular form. It has an upper triangular form. Is that okay? So this is what you have, this is what you have to be careful about, that you should know how to do it and understand these ideas, that even though I am looking at orthonormality and so on, at the back of my mind independence is always there. So if whenever I have independent thing here in example 1, when it was linearly independent here, I got Q which was of the same order as A, there was no issue, and similarly R was also of the same order or similar order you can say. But when it is dependent, then the vectors in Q become less, the number of columns in Q become less, that is equal to the rank, and you do this, all right. So this part that I had applied here is called the generalized QR algorithm. QR algorithm, and the previous one was the actual one, the QR algorithm. Is that okay? So let me write what exactly I did, all right, fine. Or let me go to one more example and then I think I can end this and then look at general ideas, all right. The next thing that I would like to now understand is what was this question we did about projection. So one example about projection example. So determine the projection of V which is 1 1 1 1 transpose on null space of A, where A is the matrix 1 minus 1 1 minus 1 1, all right. So this matrix A is 1 cross 5, and I am supposed to look at the, I think I should have written one more because it has got 5 components, there should be 5 components here also, fine. So I have to look at the projection of this, projection of V on A, null space of A. Is that okay? So let's compute the null space of A and then proceed. Is that okay? So we'll do it via 2 method if I have time. So let's see. So one is, so method 1 is look at what is null space. So null space of A, if I want to look at X belonging to R5 such that AX is 0, this is the null space of A. So this gives me X minus Y plus Z minus W plus U is 0. So I am writing X as X, Y, Z, W, U. I always do mistakes, so I will do again a mistake. So be careful. So what I get here is X is equal to X, Y, Z, W, U will be equal to X is minus Y, X is Y minus Z plus W, Y minus Z plus W minus U. Y remains as it is, Z remains as it is, W remains as U remains. So from here what I get is Y times 1 1 0 0 0 plus Z times minus 1 0 1 0 0 plus W times 1 0 0 1 0 and plus U times minus 1 0 0 0 1, fine. So I have got a basis of the null space. So a basis of null space of A is 1 1 0 0 0 minus 1 0 1 0 0 1 0 0 1 0 and minus 1 0 0 0 1, fine. This is the basis of null space, fine. That is one way of going about it. We will see the use of this. From there we will get an orthonormal basis and then proceed. So from here construct an orthonormal basis of null space of A, fine. The other way is, so as I said, if you remember that I have this space with me, I have the vector V here, I am dropping a perpendicular here. So this is 90 degree that I have. So to get this vector W, there are two ways. One is just look at the projection directly, the other way is compute this part, alright. So, if I want to compute this part, that is much easy for me, because for this plane the null space of A, alright, there is only one vector which is perpendicular to it, which is normal to it, and that is already given to me, alright. So, the normal vector of this plane, so normal vector of the null space of A is already given, alright. So, this vector, this perpendicular vector, the direction cosines of this is already given to me. I can use this to get a projection onto this, alright, on this, fine, on this vector, and then subtract it. That is another way of doing it. So, let us do that part first. So, look at projection of the vector 1 1 1 1 1 on this vector, whatever that is A for me is, fine. So, let me not write A here, so whatever it is. So, some vector which is, let me write it as U, fine. So, I want to look at this. So, this was, if you remember, this was nothing but, so this is my V. So, it is V comma U divided by length of U into U upon length of U. This is what I was supposed to do, fine. So, here if I look at this into this is give me 1 minus 1 1 minus 1 1. So, it is 1 upon, alright, this is 1 upon something, U was, this is my U vector. So, the length of this vector is 5. So, it is 1 upon, so let me write, I think otherwise there is always a confusion. So, I am writing here as 1 1 1 1 1 with 1 minus 1 1 minus 1 1 divided by root 5 into 1 minus 1 1 minus 1 1 divided by root 5, which is equal to, as I said, 1 upon 5 times 1 minus 1 1 minus 1 1, alright. This is what it is, and therefore, the vector that I am asking for, the projection vector is the V minus this projection, which is V was 1 1 1 1 1 minus 1 upon 5 times this vector, whatever it is, and therefore, this turns out to be 1 minus 1 upon 5 is 4 upon 5, then 1 plus 5, so 6 upon 5, then again 4 upon 5, 6 upon 5 and 4 upon 5. Is that okay? So, I would like you to see that this vector is indeed in the null space, alright. So, verify this belongs to the null space, alright. So, for verification what you are supposed to do? Just check whether this vector is perpendicular to this vector or not, alright, fine. So, is it orthogonal to 1 minus 1 1 minus 1 1? Answer is yes. 12 minus 12 is 0. Is that okay? The other was, look at the orthonormal basis of null space. So, I have computed that orthonormal basis, null space of A, orthonormal basis. So, orthonormal basis turns out to be, where did I write here, 1 upon root 2 times 1 1 0 0 0, or you can do, so no, I will just, because time is not there. So, try it out yourself, alright, and complete. I will give you another idea which is also important, therefore, I think I am asking you to do this. The third idea is that we have null space of A, the basis of null space of A as 1 1 0 0 0, another element was minus 1 1 and then 1 0 0 and that part minus 1, alright. So, I had minus 1 0 1 0 0, then I had 1 0 0 1 0, minus 1 0 0 0 1. So, this was about the null space of A, and the vector that was given to me on which we were looking at things, the null space was 1 minus 1 1 minus 1 1, alright. So, if I look at this, so This comes from the null space, basis of null space, and this is orthogonal vector to null space of A, or it is normal of it, all right. So therefore these 5 vectors, they are the 5 vectors are linearly independent, all right. Since these are linearly independent, I can always solve the system this is equal to 1 1 1 1 1. So the solution always exists. The solution always exists, all right. So I can solve it, and it turns out that x is equal to, so x turns out to be equal to 6 upon 5 minus 4 upon 5, 6 upon 5 minus 4 upon 5 and 1 upon 5. This is what it turns out to be. So I would like you to verify here. So verify that W vector is already 1 upon 5 times 1 minus 1, 1 minus 1, 1, and this 1 upon 5 is coming as the last entry here. This is also equal to 6 upon 5 times the first vector minus 4 upon 5 times the second vector, then plus 6 upon 5 times the next vector, and minus 4 upon 5 the last vector. Is that okay? So complete this argument yourself and verify. So there are different ways of computing these things. I would like you to try that out, all right, and learn it.